And welcome back to Math 160. You like that intro? We're going to begin our chapter 5 with a tiny review of probability. So, flipping the page, we are going to start by talking about something called an event. An event is a collection of results or outcomes of an experiment to which a probability is assigned. So for instance, tossing a coin is an event, rolling a die is an event, picking cards from a standard deck of cards is an event. And those events all have lots of probabilities, right? They all have different outcomes. A simple event is an event where all possible outcomes are equally likely to occur. So as a matter of fact, all of the examples that we expressed before. So tossing a coin, it's a 50-50 chance, right? It's either going to land heads up or tails up. Rolling a die, each outcome is 1 out of 6, because if you roll a 1, there's a 1 out of 6 chance you roll a 1. There's a 1 out of 6 chance you roll a 2. There's a 1 out of 6 chance you roll a 3, and so on and so forth. With picking cards from a standard deck of cards, there's a 1 out of 52 chance that you pick an ace of spades, right? They're very unique. It gets to be a little bit different when you talk about groups of cards like diamonds versus spades versus clubs. But if we're looking at the individual unique card, then there's a 1 out of 52 chance of pulling that card. A sample space consists of all of the possible outcomes of an event. So for instance, if you rolled a standard die, 1, 2, 3, 4, 5, 6, those are your possible outcomes. And remember, we're just rolling it once. Your sample space can grow, and it can look a little bit differently when, let's say, we're rolling a die and flipping a coin, or rolling a die and then rolling it again. Right? So your sample space grows depending on the events, depending on what it is that you're actually doing. In terms of formulas, let's take a look at something that we're actually familiar with. So we've talked about relative frequency. So we have something called relative frequency approximation probability. I know, a mouthful. It is defined as the number of times that the event occurs during experimental trials divided by the total number of trials conducted. That's a super fancy way of saying, take a look at the experiment that you've conducted. You've shown that 7 outcomes were purple, 3 outcomes were blue, 5 outcomes were pink, and 5 outcomes were orange, right? We're looking at just an example experiment that we conducted. Then we noticed that there were 20 total outcomes. So if we want the likelihood or the probability that, let's say it were a spinner. So if we want the likelihood that that spinner lands on purple, that's going to be 7 out of 20, right? Our relative frequency, which we've already done before. So 7 out of 20 is the probability or the likelihood that it will land on purple. If you turn that into a decimal, that's 0.35, and then turn that into a percent, and it's 35%. Similarly, with blue or pink or orange, if you want to find their respective probabilities, you take their frequency of occurrence, how many times did you see it, over the total number of outcomes in the experiment. So for blue, you have 3 out of 20, which means that blue occurs 15% of the time. Any questions on that concept and that tying together of relative frequency and likelihood, probability? Beautiful. Next, we have this term called theoretical probability. So it's defined as the probability of an outcome based on an understanding of theoretical outcomes and not based on results from an experiment. When you hear that phrase theoretical probability, I want you to think in theory, right? This means we're not actually conducting any experiments. So for example, in theory, if I were to say, what is the likelihood, what is the probability that you pick a heart from a standard deck of cards? What's the likelihood that the card you select will be a heart?
1/4.
1/4, yes, I love that. So what you did is you said, There are 4 suits: hearts, clubs, diamonds, spades. One of those suits is hearts, so it would make sense that it's 1 out of 4. Now, the only reason we can say 1/4 is because each, what's the word I'm looking for? Each suit has exactly the same number of cards. How many cards is in each suit?
4.
No.
Wow.
52. In each suit, Sam, yes.
Wow.
13. In each suit, there's 13. You have ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, 2. So there are 13 cards. Man, you guys got to play cards. Get a deck of cards and go play cards. Spades. You can play gin rummy. Play some games. Just get out there and please play. You need to. Okay, that's an assignment. You need to. Okay, so we're able to say 1 out of 4 because each suit has the exact same number of cards. You could have said 13 out of 52, which is interesting because if you did say 13 out of 52, it does reduce to 1/4. So 25% of the deck is hearts. Okay, but that's in theory. What I'm trying to say to you is that theoretical probability is very different from something called empirical probability, where an empirical probability, and I'll write that down in a second, refers to you actually conducting an experiment and then deciding probabilities based on that experiment. So let me write that down. We also have empirical probability. And probability is probability, right? It's the total number of successes divided by the total number of outcomes in that particular event. So with empirical probability, this is based on experimentation. It's not based on theory. That's the main difference between the two: empirical experimentation, theoretical in theory. Good. Now I want to actually answer some of these so you can shout out what your thoughts are for these. So to prove your understanding of theoretical probability, let's find the probability that you roll a 5 on a standard die. What's the likelihood that when you roll a die, it lands on 5?
1/6.
Perfect. One of those outcomes is a 5. There are 6 total outcomes. The probability of coin landing tails up in a coin toss.
1/2.
1/2.
Yeah, 1 out of 2.
Exactly, 1 out of 2 possibilities. Picking a queen or a 9 in a standard deck of cards.
8 out of 52.
Yes, 8 out of 52. There
I
are
should start playing cards.
yes, please. Please, please. I swear it's also very fun. I swear. Okay. Like you will have a fantastic time. So there are 4 queens, there are 4 9s, there are 4 of any type of card in a standard deck of cards. So 4 and 4 make 8 out of 52 total cards. All right. If we were meeting in person, we would have a card game day. And I'm sorry that we're not meeting in person, because I would love to play some of you in spades and destroy you. So, as I was saying, we then have subjective probability. So, Donna, yes, question.
Sorry.
No, go for it.
So how did you get 1? Like A?
Oh.
How did you get A?
Think about when you roll a die, right? It only has 6 sides. And on that die, you have 1, 2, 3, 4, 5, 6, the numbers. So if you want to roll a 5, do you agree that only one of those outcomes will be a 5?
Oh, okay, I see.
Right? Yes.
Yeah.
So one of those outcomes is a 5, and there are 6 total outcomes. So that's why it's 1 out of 6. It doesn't matter
Okay.
about the number itself. Like I could have said, what's the probability of rolling a 3 on a standard die? You would be like, oh, 1 out of 6, because there's only 1 3 on any die.
Okay, thank you.
You're very welcome. Excellent. That's always the thing that tends to kind of throw people off a little bit, is that idea is like, wait a second, there's a value here, but it's just a position, right? It's just an actual outcome.
I think what it is that maybe I just didn't know like the terminology. You know, I'm still like new to this American
Yeah.
terminologies. Yeah.
No, I got you covered. And by the way, if there's anything where you're like, I am not familiar with this kind of thing, please let me know. I would love to break it down. Like if we could meet in person, we would be playing with dice. We would be playing with cards. Like, I'm not even kidding.
Thank you.
You're welcome. Excellent. Subjective probability. So it's a type of probability derived from an individual's personal judgment or own experience about whether a specific outcome is likely to occur. We've done this all the time. You ever have that friend who you love? They're your friend, obviously, but you know that 9 times out of 10, when they say they're going to be somewhere, they're not.
Yes.
Okay. That's subjective probability, where you're like, unfortunately, don't bank on that person being there. I'm already going to put money on the fact that they're not going to show up. There's a 90% chance that they're not going to show up. So you do these things very naturally already. That's just subjective probability. It's based on your experience and what you've kind of seen for yourself. I like that because it's so true for all of us. There's always that person. And sometimes we are that person. So I gave you 2 examples here. A business analyst predicts the chance employees will go on strike is 20%, right? And this kind of stuff happens all the time where you have someone looking at, the data, they're looking at morale, they're looking at the way in which people are calling off of work and things like that. And they're able to provide some sort of statistical theory or probability in terms of what's going to happen next. Like, will our people go on strike? Is productivity going to go up, depending on, X, Y, or Z? So a lot of this happens. A sports fan believes the chance his team will make it to the playoffs is 70%, right? This is definitely something we see a lot of the time as well. Fantasy football, that kind of thing. That's why we pick based on our own experiences. We have something called the law of large numbers. And very simply put, what this is saying is that if you were to conduct an experiment, right? Let's say you were taking a coin and you were flipping it and you just kept flipping it and you kept flipping it. Chances are, if you took that coin and you only flipped it like 20 times, you may not have equal parts heads up, tails up. Chances are, if you conducted that experiment right now at home, one of those outcomes is going to be much greater than the other. As crazy as that might sound, because you would feel like, but wait a second, there should be a 50-50 chance. Literally, that almost never happens with a small number of trials. However, the law of large numbers shows that if you were to keep doing that, instead of 20 trials, you did 50 trials, or 100 trials, or 1,000 trials, that as you conduct this experiment more and more and more, you get closer and closer and closer to the actual theoretical probability. If you don't believe me, you should try this out. Flip a coin 20 times. Record the outcomes. I guarantee you, you will not get 50-50. But if you were, and you don't have to do it 50 times, but if you were to do this 50 times, then you're going to be a lot closer to that 50-50 outcome. Crazy, right? That's a law of large numbers. If you open your PDF on your computer, this particular guided notes PDF, you can click that link and it shows you an interactive simulation of the law of large numbers. It's pretty cool. If you're nerdy like me, I was like, oh yeah, I'm going to include this because this is pretty neat. Go ahead and click it, check it out, nerd out a little bit. I think it's cool. So take that with a grain of salt. All right, let's turn the page. Next, we have something called the multiplication rule, which obviously tells you what we're going to do. So if we want to determine the probability of one outcome, and then another outcome occurring, we use a multiplication rule. So here's something that's really important for you. Can you underline one outcome and then another outcome? When you hear that word and, you can pretty much guarantee you're using the multiplication rule. Okay. The probability that events A and B both occur is equal to the probability that event A occurs times the probability that event B occurs, given that A has occurred. So we're basically saying that when we find this probability of the first event or the first outcome and then the second outcome, you can basically say it's going to be the product of both of those. So you're looking at successful outcomes. So the probability of A and B is going to be equal to the probability of A times the probability of B. And that's how you would write it out. Okay, the probability of A and B is the probability of A times the probability of B. Under this idea, we have something called independent events, and you'll know that two events are independent if and only if the occurrence or non-occurrence of one of the events does not affect the probability of occurrence of the other event. Here's what I mean by that. Is it possible for the chance of rain to impact the occurrence of whether or not I drink that coffee right now?
No.
Probably not.
Probably not, right? It seems highly unlikely that that weather would have any impact on whether or not I'm drinking coffee. I'm drinking coffee. I'm going to do it, right? So those are independent events. There's no way for one to really truly impact the other. That's what I want you to think of. And I wanted to give you something, an example that was so ridiculous that you could be like, obviously, whether it's raining or shine or whatever, she's gonna drink her coffee. Like, I know that sounds stupid, but I'm just trying to drive home a point. Okay, cool. Let's take a look at a practice problem that involves a multiplication rule. So bear with me. What I think is going to be helpful, especially for those of you who are not familiar with a standard deck of cards, I'm going to write a few notes. The first thing is that there are 52 cards total. Okay. There are 4 suits. You have spades, diamonds. If you know cards, you don't need to write this down. Hearts, and then clubs. And then there are 13 cards in each suit. I'm very curious, show of hands, how many of you are very comfortable with a deck of cards? Cool, very nice. Okay, so a pretty decent chunk is comfortable with a standard deck of cards. Leah says, awesome. Please play cards. It's fun. Please do it. Okay, very cool. I was just curious. So hopefully this information is helpful. Keep in mind that if there's a 2 of spades, there's a 2 of diamonds, there's a 2 of hearts, there's a 2 of clubs. So it's just to kind of give you a little bit of an idea with these cards. So there's going to be 1 of each suit. All right, let's begin. We would like the probability of selecting 2 diamonds from a standard deck of cards without replacement. So there's a few things we need to know. We want to select 2 diamonds and it's without replacement. So we mean we're not putting it back. So let's pick one card and then the next. What is the probability that the first card you choose is a diamond? Anyone?
13 out of 52.
Perfect. The probability that your first card is a diamond is 13 out of 52. Okay, you were successful. You picked a diamond. Now you put that card, remember you just picked one card, you put that card in your back pocket, and then you pick your second card. What is the likelihood that the second card will be a diamond?
12 out of 51.
Yes, nicely done. 12 out of 51. Excellent. I hope that visual was super helpful. You started with 13 diamonds, you picked a diamond, put it in your back pocket, go back to the deck of cards, pick again. There's a 12 out of 51 chance now that you pick a diamond. All we have to do is multiply straight across. So would somebody give me the numerator of our fraction? Go ahead and shout it out.
156.
Yeah, excellent. 156. And someone else the denominator.
2,652.
Perfect. If you were to turn this into a decimal, let's punch in 156 divided by 2652, and we get this number here. So we see that it is approximately equal to, and I'm going to round to my thousandths place. So three values, 3 places after the decimal. So we've got 0.059. If we turn that into a percent, we have to multiply that by 100 or move the decimal over 2 places. And we could say that this is the same as having a 5.9% chance. There's a almost 6% chance that that's possible, where you pick a diamond and then you pick another diamond, having already kept that first card. So it's pretty low. It's a low likelihood.
So did you use 12 because you would take away 1 from 13?
Yes, that's exactly why. I want you to literally visualize taking that card that's a diamond. It doesn't matter what it is. Taking that singular card and put it in your back pocket. Gone. So then when you go back to the deck, you're like, well, I only have 12 diamonds left out of the 51 cards that are left. Definitely visualize. That's going to be super helpful. I want you to try part B, selecting 2 diamonds from a standard deck of cards with replacement. Just think about that for a moment. Send to me your answers in the chat. And I just want the fraction form, please. I'm going to pause the video. Okay. So the probability that you select a 10, well, there are only 4 10s in any deck of cards, right? So it's 4 out of 52, and that's for your first pick. That's your first card. Now you pick the card, it's a 10, put it in your back pocket, go back to the deck and now pick a jack. Well, there are still 4 jacks in this deck of cards. We have not picked a jack at all. So there are still 4 outcomes, but this time there's only 51 cards. It was without replacement, so we kept that first card, which is what decreased the denominator by 1. When you multiply from left to right, you'll have 16 over 2,652. Excellent work. Excellent work. I loved all of your responses in the chat. When we punch this into our calculators, we get a value of 0.006. If you multiply that by 100, that means you move the decimal only twice. So the likelihood that that happens is 0.6%. Crazy, right? There's a 0.6% chance, less than 1% chance that this will happen, where you'll pick a 10 and then a jack without replacement. Good. What questions do you have for me on practice problem number 2? Mallory, talk to me about this. What did you get for your setup? First card, second card.
I had the exact same thing as you.
The 4 out of 52 and then the 4 out of 52.
Yeah.
Perfect. So yeah, if you just went left to right, 4 times 4 is 16, 52 times 51, that should give you the 2652. And then take this and divide to get that value. But yeah, you and I have the exact same values. Good. Good, good, good. Turn the page when you are ready. Look at part D. The probability of rolling a 2, rolling a 1, and rolling an even number on a standard die. Try this out. I would love to see how you tackle this. Remember, it's one, then the next, then the next. So you obviously are rolling 3 times, so you should have 3 different probabilities. Think about this. Go for it. Let's check this out. Let's investigate this whole. We're going to do that together. So the likelihood that you roll a 2, there's only 1 2 on any die, right? There's only 1 2 on any die. So the probability of rolling a 2 is going to be 1 out of 6. Be careful. It isn't 2 out of 6 because there aren't 2 occurrences of 2. Think about a die, holding a die and then looking at all the sides. You only see a 2 on one of the sides. The probability that you roll a 1 is 1 out of 6. Again, there's only one outcome of 1 on any die. And then the probability of rolling an even number. Well, there are 3 even numbers on any standard die. So it's going to be 3 outcomes out of the 6. Think of your denominators in each fraction as being your total outcomes. If that's weird to you, let's write out the outcomes on any standard die. So no matter what happens on that die, you have the outcomes 1 through 6. So there are 6 total outcomes. Your denominator for your fraction will always be the total number of outcomes. Your numerator is the number of successes. So how many even numbers do we have? Well, we have 2, 4, 6. We have 3 successful outcomes out of the 6 outcomes total. We then go ahead and multiply from left to right. So our numerator is 3, 6 times 6 times 6, that's going to give us 216. If we took 3 and we divided it by 216, you'll find that you get rounded to the nearest thousands place 0.014. So I'm going to write here that this is approximately 0.014, which means that there's a 1.4% chance that this happens. There's a 1.4% chance that you roll a 2, then you roll a 1, and then you roll an even number. You can think about these probabilities when you play Yahtzee, right? And you're trying to get all those different combinations. By the way, if you haven't played Yahtzee, don't feel bad. I just started playing Yahtzee like a year ago. I didn't really even know about it until then, which is kind of crazy. But it's fun. You should try it out. Okay. Any questions so far?
I still don't understand.
That's okay. What part is throwing you off?
I don't know everything. Everything.
Here's what's going to help. Can you write down that probability is success over total number of outcomes? That's what probability is. It's just the success over the total number of outcomes.
I usually do well, like if I'm reading like a book, you know what I mean? Like if I'm reading it
Yeah.
and I get more information, but because we're not using a book, it's like,
Yeah,
you know.
we're basing it off of our previous knowledge of like dice and cards, and that can make things a little bit tricky, especially if we're not really exposed to those things on the regular. What I would advise you to do is, if you're thinking about these problems and you're trying them in Lumen, like what I did, I pulled up a visual of those cards, or grab a deck of cards. Grab a die, you know, like a set of dice. Grab something just so that it's more tangible, so you can kind of play around with this idea, as opposed to just, you know, visualizing it. No worries, Lainey. Okay, so I would definitely advise getting your hands on decks of cards and on dice to kind of play around with all this stuff. Okay, Donna?
Okay, thanks.
And then in the meantime, still reach out to me and ask questions if you're curious. And we can definitely tackle this and make sure that you're feeling much more comfortable. Okay,
Thank you.
you're welcome. Now for part E, I actually wanted for this to be more dynamic and based on all of you. So I think the best way to do this is to get the responses in the chat. So I would like to know how many of you were born in the summer. So if you were born in the summer, just type in the chat me, and you can send it to everyone because we need to do a count. So Lucy, that's one, Kelly, Ava, Nick, Anthony, Holly, Jenny, Lucy, am I counting you twice? Mallory, Carrie, Surujini, that's 10 so far. Anyone else born in the summer? Okay, it looks like it's just 10. So 10 out of 28, because we're not including me, I would be the 29th. So we're gonna say 10 out of 28, right? There are 10 people who were born in the summer out of the 28 students that are in this Zoom room right now. Okay, now let's start again. How many of you played on a high school sports team? Ooh, okay. 1, 2, 3, 4. Oh my God, holy crap. Okay, let me scroll right back up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. It looks like there were 13 of us that played on a high school sports team. So because we want the probability of the first one and the second, we go ahead, multiply these two together, and we get 130 out of, let's do 28 times 28. That's going to give us 784. Why does that seem low? Nope. That seems super low to me. 784. If you take your fraction and divide it, round it to the nearest thousandths place, we get 0.166. So that means there is a 16.6% chance that someone from this class was born in the summer and played on a high school sports team.
I
have
have
a
a
question.
question.
Yes, go for it.
Sorry, you go first. Angelica, you go first.
Sorry, my thing accidentally went in the chat and is just doing a bunch of spaces. But how do you know? Because when I read it, a student from the class that was born in the summer and played on a high school sports team. When I read that like it would be out of the people who were born in the summer.
Yeah,
So-
same.
Yeah, I totally get that. So when we're applying the multiplication rule, I know you're thinking, well, shouldn't we actually pick like the people who were born in the summer and then look at those and then say how many of those people played high school sports team? That would be a conditional probability. But in this case, we're just looking for the probability of the first event and the probability of the second event. So we're looking at these as two separate probabilities, so to speak. Also consider that there's no with or without replacement, so to speak. It's just saying, let's take the probability of the first event and then the probability of the second event, and in which case you would multiply those. So it's interesting because we're about to look at a conditional probability, which hopefully won't freak anybody out because it has a very interesting way of looking at probabilities. So I think maybe if we looked at that, you may feel a little bit more comfortable with what we just did. Let's try this out. Conditional probability. This is the probability that event A will occur given that event B has already occurred. Notation for finding the probability of event A given event B has occurred is written as the probability of A given B. Okay, that's how you would write it with that vertical bar. So let me show you an example. Hopefully this is not like too crazy. You roll a fair die. Let A be the event that the outcome is an odd number. So that's the first thing I'm going to consider. We want event A to be an outcome that is an odd number, right? On a fair die. So we know that for event A, the outcomes are 1, 3, 5. Then you want to let B be the event that the outcome is less than or equal to 3. So I'm going to highlight that as well. B is the set of values where the outcome is less than or equal to 3. So B is 1, 2, or 3. So what is the probability of A given B? So this is a little bit of an interesting take to this. The first thing I want you to consider is that we know that the set B is equal to the outcomes 1, 2, and 3. So we want to know the probability of A. Now, A is that the outcome is an odd number. Now, because it's conditional, stating that B has occurred, this is when we say, well, okay, let's look at set B, which only has 3 elements. What is the outcome that we have an odd, or what is the chances that we, wow, I can't talk. What are the chances that our outcome is an odd number? And we're going to say, well, only 2 out of the 3. So we see that the probability of A given B is 2 out of 3. So now we're looking specifically at this set that we have for outcome for event B. And we're saying out of those values, how many of those outcomes will be odd? And it's going to be 2 out of 3. Does that make sense? Conditional probability. How now we're looking at a subset, and then based on that subset, we say, well, what are the chances we'll have an odd number? I'm going to write one thing underneath here. We know that B is a set 1, 2, 3, but set A represents odd numbers. If we're looking at set B, only 2 of those outcomes are odd. So the probability of A given B is going to be 2 out of the 3, because remember, it's a condensed set. We're saying that B has occurred. And that's the difference between the multiplication rule and conditional probability. What questions do you have for me? Hopefully I'm not freaking you out. While you're thinking about this, I want to look in our Lumen course. Take a look at your Unit 4 probability. There's a few examples here, a few homework assignments here that pertain just to the Unit 4 homework assignments. And I just want to show you what you have coming up. So first you have just basics of probability, which I think honestly for all of you, this is just going to be a really nice way to make sure that you're understanding the basics of probability, right? So you're looking at spinners, you're looking at a standard deck of cards answering probability, same thing for the rest of these questions. So it's not too bad. Here we have a table of values, and we're going to use this information to help us find probabilities as well, which I think is hopefully going to be pretty straightforward. If not, please don't hesitate to reach out. I will be happy to help. Next, we have calculating or and probabilities. So what we're essentially looking at is we're going to be looking at conditional probability, as you see here. We're going to be looking at lists of outcomes, and then based on our sample space, we can answer probabilities, things like that. And then we have an application problem for unit 4. So let me show you something. Remember how I had commented about the fact that, I really want you to play cards? Here it is. So your unit 4 application is called "The Probability of Fun is High with This One." Yes, I'm a nerd. Sorry. That's just how I am. That's how my brain works. I'm a huge nerd. Okay. For this assignment, you must either learn a new card game. Yes, you're going to play, or you're going to teach a new card game. So if you already, have some card games you love playing, I want you to teach someone a card game. If you don't know any, talk to somebody. Guaranteed you'll find someone who plays cards, and then they can teach you. To get the full 20 points for this assignment, you're going to have to answer each of these parts. Okay. What's the name of the game? What's the general gist of the rules? You don't have to go super crazy with this, like listing the whole thing, unless you want to. But I'd prefer if you just give me a general gist of the rules of the game. Tell me how many people can play at once. Like with spades, only 4 people can play, right? So that kind of thing. Hearts, only 4 people can play. Actually, I think that's false. I'll come back to that. How do you think probability plays into how someone can win? So as you're learning this game, think about what strategies you use to win the game. And then think about how that relates to probability, right? Think about winning and how probability comes into play. Is it easier to win or to lose? So that's something that's very interesting to think about. Like, are you more likely to win? Are you more likely to lose? Like, what would be the scenario? What would help you to win more times? Or what would contribute to a loss? That kind of thing. And then, if you learned how to play, talk about the experience. Who taught you and what was that like? If you taught someone how to play, who did you teach and what was that experience like? So this particular application is really intended to just get you using a standard deck of cards, playing around with this, and really connecting to the idea of probabilities, of likelihood of something happening, right? And as we play these games, we always want to win. So the probability of us winning, all right? I want you to think about that perspective. Any questions on that so far? Cool. Hearing none, I would like to come up with due dates for our Unit 4 assignments. So by the way, I'm done teaching for today. I'm just going to come up with due dates. So when can we have our basics of probability due? What do you think? Today is the
I got a
29th.
question.
What do you think? How much time do you need?
If we're just now starting it, what about October 20th?
Okay,
Or
so that gives you 1, 2, 3 weeks to do these assignments. I mean,
the test is the week before that.
that's true.
So
The
What about the 14th or 15th?
the 14th or 15th, I feel like that sounds much more reasonable.
Because everything else we have due is due on the 13th.
Right.
That's what I'm saying. I think that's kind of too close, but I don't know.
What
So, like,
about giving you that additional weekend? How about the 18th? Can we compromise?
Yeah, I
Yeah.
like the 18th.
The 18th is
Yeah.
it.
Score. So let's do the 18th for those assignments. So there's the first one. Same thing with calculating and probabilities. I'm expecting that there might be a few questions, and that's okay. So what we can do is, as you're working on these assignments, at some point, if you do have any questions about that, let me know. We'll look at it as a class. I think it's going to be really, really helpful to do that. So let me assign this one for the 18th as well.
And it gives us time to learn like a card game if we need to learn.
Yes, yes, exactly. Does everyone have an idea of who they might talk to for that?
I have 3 kids if anybody needs volunteers.
Excellent. You're just gonna pass them out. Go play, go play, go play.
I got a question.
What's that?
I got a question.
Yeah.
You see that the Lex assignment that you was explaining, when is that one due?
Those 3 are due on the 18th, so you have plenty of time. Almost
All
3.
right. Thank you.
You're welcome.
I have a question. Can you show us where the test is? Like where I can, I
Yes,
think I
so
was playing around and didn't see
let
it.
me see. It just showed up today. So your first test, let's see, is it still hidden? There it is. So it is in unit 3 homework. It shouldn't be there. I'm going to move it. Give me a second. I'm going to move that out. I don't want it to be in the actual unit 3. So I'm going to move this out. So now you should see it. If I close unit 3, there it is. So it's right underneath unit 3, but above unit 4. All right. Now you should see it. You may have to go in and out of Lumen since I just made this update, this change, but you'll see it right in between the 2 blocks.
Yeah, thank you. I was
Professor?
just looking before and I couldn't
Yeah.
see it. So
Yeah, it was just in unit 3.
If I'm not mistaken, you said we have 3 attempts at the test, right?
Yep.
All right.
Yep.
Thank
And
you.
it will keep your best score. So don't worry about anything. Let's say you do great the first attempt and then you're like, oh my God, I made some silly errors or second one. It will keep your higher score.
All right. Thank you.
Somebody said there was a issue on the unit 3 homework. Did you-
Yes, unit 3, the second homework assignment, problem number 7. So if you look at the unit 3 homework, understanding z-score and range rule of thumb, that problem 7, when you do it and you do it correctly, it's only going to give you 2 out of 4 points instead of 4 out of 4, even though there's only the 2 spaces here. So I'm going to go in and I will give you those points back. But
Gotcha.
I've been sneaking in there, and anytime I see answers that are correct, I've been giving full credit, but I'll definitely do that when this is officially due. After it's turned in. Okay.
Thank you.
You're welcome. All right, I'm gonna stop the video here. So that concludes our, give me 1 second.
Oh, I'm
Okay.
sorry.
That's
Sorry.
okay. That's okay. I'm going to conclude our video here. So make sure that you are practicing that probability over the weekend and completing all your unit 3 material. Excellent work today.